we've gone through Democritus, whose atom basically looked like a triangle or a sphere. We saw Dalton had different size, kind of spherical atoms, you know. Different elements had different, you know, sizes and masses. And we saw J.J. Thomson came up with the positive and negative. Somehow, actually, let's do his poem. It was more the Chips Ahoy, right? So in Thomson's cookie model, the cookie dough was positive and the electrons were negative. Rutherford shot the alpha particles through the gold foil to test out this hypothesis. And he found that because 1 out of 20,000 of these alpha radiation particles, which are really heavy, high energy, 1 out of 20,000 got bounced directly backwards, that something very dense and repulsive must be in the center of the atom. So he said, take all of this positive cookie dough and shrink it down to a very small area, and then put around that all the negatives, and then in between this is just empty space. Right here is empty space. And that would allow the bullets to basically go through unless they came close to the nucleus, which would then bend it or bounce it backwards. So this is Rutherford. This is Rutherford. Rutherford was Thomson's student. So we kind of have like grandpa, dad, and son here, because Thomson was the grandpa. He was the teacher of Rutherford. Rutherford's like the dad of Bohr. And we're going to talk about how did Bohr come up with his planetary model. This is what everybody makes in like middle school or elementary school. That model of the atom where they put the electrons like planets going around. If you say, no, we didn't. Oh, I'm sorry. The teacher stuff. I mean, you should have. You know, somebody made, that's more like a Rutherford model there. Is that something in this class made there? Somebody brought that into the rap battle. They said, were we supposed to make our own? No, it's on a rubric. I said, well, you can have it. So that's kind of like the Rutherford model. The central positive region surrounded by the negatives that are all on the same basic level. So Ethan, you got to put your phone away. Guys, put your phones away. If you're setting up your hotspot, set it up and put it away. I can't teach you if you're yakking away at somebody else. Or vice versa. So how did he come up with this model? Why, how did he go from this to this? Turns out he used light. The fact that different elements give off different colors of light. So let me get this. I think for this, I used to have this hung up and then everybody kept going into it. Oh, so if you look at all these different elements, you'll notice they all have different patterns of light. Where does that come from? If you take sunlight, and shine it through basically a prism. Well, this is kind of a prism. Take sunlight, pass it through a prism, you get a rainbow. And that's why when it's raining, they call it a rainbow, because every little drop of water. Can you put that away, folks? Though? Thank you. I'm pretty sure I said put it away. Each little droplet of water is acting like a little prism, and sunlight goes through it, gets bent, and depending on where you're standing, you see one part of the red, orange, yellow, green, blue, indigo, violet colors that make up red, orange, yellow, green, blue, indigo, violet, make up the sun's light. And that's why it looks like a bow, because you're seeing billions of droplets of water, but only some of them are at the right angle to show you different colors. Not all of them. So it makes a bow around you. If you could see it in space, it would be a complete 360 circle. So in order to get this model of the atom, Bohr was taking elements, pure elements, or in some cases, salts of elements like sodium chloride, potassium chloride, which is called sea salt, magnesium sulfate, which is Epsom salt. You can take different metals that are in salts, and you can dissolve them in water, and then you can take a little spray bottle and squirt. We're supposed to do this live. We'll see if we can. We've been a little busy with winter break and now an exam, but maybe when we get back, we'll do this live. You spray the salt water into a flame. We'll trigger there. As it sprays into the flame will give off some color of light. The flame will change colors depending on what element you're squirting into it. If you then take and pass this light through a prism, that light will decompose into the constituent or the colors that make it up. You'll find that almost all of them have. I should have put. Let me do something. I'm going to put that yellow between. Here. All right, so as you shine the light given off by an element straight into a flame through a prism, if you project it onto a photographic film, you can take a picture that will look like this. Now, by the way, the actual shape of the line will look like the shape of the object producing the light. So these straight up and down lines were produced by, instead of a flame, they were produced by what's called a cathode ray tube, a Crookes tube. You remember J.J. Thomson used one of these to study and come up with the electrons. Well, it turns out if you change the gas inside there, you'll change the colors and therefore the patterns of light. And the light coming through the prism will actually look like that light, it's just be in a different color. Typically what they do is they take the light and they pass it through a cardboard paper with a tiny, tiny razor cut slit in it, so it does look just like that. So what Bohr realizes, every element is different in the color light it gives off, and when you break it up, it's it gives off a different pattern. You can see right here, helium, hydrogen. Everybody has a different fingerprint of light. Now, astronomers today use that information. They'll take a telescope, point it at a star, and they'll take the light that comes from that star and pass it through a prism and separate it into its different components of colors. And you can actually tell from that which elements are in the star. Depending on how bright they are, you can then depend how much of that element is in the star. And based on the idea that all the elements are made simply by fusing together one more proton, one more proton, one more proton. 1 and 1 is helium, 2. 1 and 2 is lithium, 3. 1 and 2. 2 and 2 is 4, which is beryllium. 2 and 1 is lithium again. Once you get lithium, you get 3. You can fuse that with 1 and get beryllium. You can fuse lithium 3 with helium 2, and you can get boron, etc. So depending on the colors of light that come out of stars and how bright they are, we can tell what elements are in them, how, what percentage based on the brightness of those lines. You can get the more of the element there is, the brighter its spectrum is going to be. The dimmer it is, the less of it there is. We can actually then figure how far along in the age of fusion that star is by what it has produced. So we can get an idea how old stars are.
Is that how we can know how old stars are?
Yep. Yep. There's several ways, and that's one of the first ways. Is once we realize that fusing single protons together makes helium, and helium makes beryllium. We can guesstimate based on what colors of light you see in the star's spectrum how old it is by figuring how far along the fusion process is. Now they do a lot with astronomy. It's pretty amazing. You can get all that and start looking through the telescope. All right. So there was a guy named Max Planck. You want to write this name down, and you're going to write his formula down in a minute. Max Planck studied colors of light. And he kind of sensed the same thing you kind of sense, and we put it into practice in our daily lives. You go to the beach, you put sunblock on to protect you from what? What kind of UV, ultraviolet. You're not worried about red light. In fact, at sunset, everybody looks at the reddish light coming from the sun and says, "Oh, how beautiful the sky is so red." We're not worried about red light. You never stare at the sun except for at sunset when all the other colors are filtered out except for red. If you go into a photographic studio where they're developing film, what color light do they use? Red. It's low energy. It won't develop the film. It won't produce the chemical reaction. It's so low energy. If you're out hunting, or if you're in the military and you're out on a night operation, you wear lights that are low energy. They're usually red. Like we were out this weekend camping with hunters and teams and some of us had white lights on. When you go look at somebody at night and talk to them, they're like, "Oh, you're blinding me," and then you can't see anything for about 30 seconds afterwards because the white light is made up of several colors of light. It actually burns an impression into the retina. Don't you put your phone away, please? Thank you. I'd really like you to listen to my little story today, so you get educated about chemistry, at least this aspect of chemistry. So these, the more prepared, more experienced outdoors people will put on a red light, or at least they'll click it so it goes to red. Because when you look at somebody with a red light, it doesn't ruin their night vision. If you watch certain special forces movies or documentaries, they'll show people in command centers at night with red lights on, because again, it won't ruin your night vision. So we know that red light is low energy, and violet light is the light that we're worried about when we're at the beach. Violet light has enough energy to punch through your skin and cause damage to your DNA, which could then either cause tumors or something else. So Max Planck studied this concept that the different colors of light have different energies. Roy G. Biv. What he did was he took basically a photocell. Many of our calculators have them up top. These convert light to electricity. Now these are pretty non-discriminating. They'll take pretty much the broad range of color coming out of this and convert it to electricity. But you can actually use different materials that will only respond to certain colors. And then you can hook them up to a voltmeter and shine light on it so that only the red light is being detected, or only the orange light, only the yellow. Or you can put filters. If you know about photography and filters, you can filter the light as long as you increase the intensity, so you maintain intensity strength instead of decreasing it with the filter. You can then measure energy as a function, or see how energy depends on color of light. And what Max Planck found was that the energy of light was pretty much linearly related to the color of light. It's a nice straight line, more or less. And if you're in math class, your math teacher might ask you to find y equals mx plus b, right? I'd like to do that kind of thing. Find y equals mx plus b. Wait a minute, I asked you to do that too at the beginning of the school year. The problem with finding y equals mx plus b is m, the slope, is the change in y, which we measure in joules, it's a number, over the change in x, which is a color. How do you subtract red minus green minus yellow, or green minus orange? Well, you can't, not with words. Yes, that's what you do. So it turns out that red light is very long wavelength, and violet light is very short wavelength. Now, from peak to peak is called one wavelength, where that just means the length of the wave. It doesn't have to be peak to peak. It could be valley to valley. It could be any two identical positions on two adjacent waves. The distance between that is called wavelength. And the symbol for that looks like an upside down Y. It's called lambda in the Greek alphabet. And the reason why we use lambda to measure the length of the wave is because it's a wave thing instead of a particle thing. A particle thing is like a baseball. You throw a baseball, you can predict where it's going to start. And when you see where it starts, And depending on how it's thrown, you can predict where it's going to land. It's a parabola. It flies like an upside down U. And people are so good at it. They're playing baseball at night. They can hear the crack of the ball, the bat, they see the ball, and then when it goes above the lights, they lose it in the darkness for a minute or two, not a minute, but a couple seconds. They still catch it like, because it's very predictable. That's called particle physics. We use, and we're as macroscopic, mostly particle-based organisms. We deal with rocks, spheres, these are all particles. Dolphins and bats deal with both particles and waves. Dolphins and bats use sonar waves. They emit sonar. What is it called? It's a sound. What's that?
Echolocation.
Yes, echolocation, but I'm trying to, there's a name for the frequency they use. I don't know what it is. It doesn't matter. They emit sound waves, and the waves bounce off things and come back, and they have a brain that is developed to process wave information, but we don't have that yet. Most humans that I know don't find their way around by chirping. If they did, we would never go to prom, right? So, maybe in the nerd group. Most of us use visual and auditory, which I guess is a type of wave. We go to public, so they'll look both ways, hopefully. It'll be like some of the dumber phrase and students are knowing the risk. They stepped out into streams of traffic without realizing choices have consequences. Actions have consequences. Step in front of a moving car, you will be run over.
Do you know, like,
I've seen students get hit.
because it happened last week to my
Yeah, I
car.
know. I saw one girl get hit. It was raining. She ran out in front of a car because she wanted to get wet. Car couldn't stop. Boom. She was okay. She fell on the ground, jumped up, and ran off. You know how you fall in public and you act like it didn't happen? That's what she did. I'm sure she was one.
So it's kind of like me when I trip on my front.
Back to echolocation and whatnot. But we don't do that. We think of the world in terms of particles. We look down the road, we see a particle coming at us, we judge its speed, its distance, and we make a decision. Do we have time to cross the road or not? Anyway, but when you start learning to describe waves, they use similar properties like length. And what they do is they convert from the English letter for particle length or speed, v, they use the Greek equivalent. So L, that's the Greek letter L. It still refers to length, but because it's in Greek, you kind of get the idea that they're talking about waves. Just a little sidebar information there. When we talk about waves, we usually use Greek letters to describe its features. Now, notice down here that violet light is very short wavelength, and red light is long wavelength. Now, there is an inverse relationship between the length of the wave and the word that, was it Nicholas threw out? Frequency. Frequency means how often something occurs. Like, how frequently do you eat? 3 times a day. Some of you eat 5 times a day. It's how often does something occur. So when we talk about the frequency of a wave, what we're talking about is how often does the peak go by us. And you can tell that a longer wave, like a red light, if this was a wave at the beach and you're standing here and you're having a great time with your bestie, holding hands, maybe smooching a little bit, and these waves are going by, it's just like, oh, it's so romantic here at the beach. You're going up and down every maybe 1 or 2 minutes. It's not a lot. And then a jet ski goes by, and of course, jet skis make these really small, close together waves, and they end up rocking. If you're ever out fishing or whatever, and a jet ski goes by, people end up yelling at them like, "Hey, slow down or keep away" or whatever, because they create these really small wavelength waves that make your boat shake. Because the thing making the wave is small. The jet ski is small, so it makes small waves, but with lots of energy. So here's what I'm trying to say: if you're in those waves, it's no fun. You're gonna be like jarred and bumped and like that. Let's get out of the water. And here's what you're detecting: you're detecting the frequency. Longer waves have lower frequency. Smaller waves have higher frequency. In other words, the smaller wave, the more can pass you in a given moment. The smaller the wave, the more can pass you in a given moment. That means smaller waves have higher frequency. Bigger waves have lower frequency. It's an inverse relationship. So the relationship between length, lambda, and frequency symbol looks like a italic V. It's actually the letter N in Greek, nu, but they chose it because it looks like V, the Greek version of V. Relationship between length and frequency is inverse. It's not direct. We just said that. Really long waves pass you slowly, or fewer per moment. What's that? The length and frequency are inverse. The longer the wave is, the fewer will pass you in a given time. Shorter the wave is, the more will pass you in a given time. If you thought about motorcycles versus semi-trucks as waves, motorcycles versus semi-trucks, maybe you're learning how to drive, you're on the highway, mom's in the passenger seat, she's like, give some gas, get on the expressway, go, faster, it's called expressway for a reason, push it, she's telling you, adjust your mirror, all right, great, she teach you how to drive. All right, so you're driving along in the slow lane, and here comes a semi-truck passing you. The semi-truck, I don't know how long they are, 150 feet long, anybody know? What? 140? So it's passing you, and you're like in a 25-foot car. It's like, and it takes forever to pass you. You're like freaking out, like, oh, you're just like, Okay, so it's a long vehicle. And so if there was a train, if there was several of them coming, you wouldn't be able to get past in 1 second like many of them. You wouldn't get past in 1 second like any of them. It would still be passing. You'd be talking about minutes, like, oh, 2 of them passing in 1 minute. But then you've seen this, there might be a bike day or something, and you're driving down You know, the interstate, and all these guys are going to Daytona for biking. And it's just a whole pack of motorcycles. It's like, round, 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 round. They're just passing. And that's because they're small. And so with smaller vehicles, more of them will pass you in a minute than, say, larger vehicles. And again, that just illustrates there's an inverse relationship between size and frequency. The bigger something is, the fewer per moment can pass you or can occur to you. So that's how waves are. And the equation that shows this is this. C equals lambda nu. Now, lambda, we said, is the length, and nu is the frequency. Now, why is that equation? What is the letter C? C is the speed of light that Einstein's equation has. E equals mc squared. It's the speed of light. If you rearrange that equation, you get C over lambda equals nu. And now you can see its inverse. Nu is on top, lambda is on the bottom. If nu is bigger, lambda gets smaller. If nu is smaller, lambda gets bigger. Inverse relationship. All of that goes into this. How do you figure out the relationship between energy and the color of light? Well, Nicholas said 15 minutes ago, use the frequency. So the color itself, you can't find the slope of this line by taking one energy and another energy, subtracting that you can do. But how do you subtract green minus yellow? You can't unless you know the frequency. So that's what they use. They use the frequency for these colors. Now, that means you can convert the colors of light into numerical values called frequency. And this kind of answers that trick question, Caroline. How do you know that the blue you see is the same as the blue I see? What? Gabriel says you can't know, you say you can't know. Well, you know, you could argue that this isn't the answer, but you could also say, well, since we don't know what blue is in color, but we do know what it is in number, we can ask people if they recognize. You know, we can ask two different people. We can show them three different colors with a number next to it of its frequency. We can actually measure the frequency of blue light, red light. You know. So if everybody chooses the same frequency, then we can be sure that we're at least seeing. You know, but then it doesn't prove it, I don't think, because if you grew up calling blue light green light, maybe not. Maybe blue light looks like green light to you in your brain, but everybody calls it blue light, so you call it blue and you think green color is blue. I don't know if that makes sense. The point is, we can kind of figure out if we're seeing the same color by using the frequency. I was trying to disprove that just now, but I don't think it can. So if we give the frequency, and frequency is how often something happens per unit time. How many times do you eat per day? 3, 5, whatever. Per unit time. And this unit here is per second. Per second. How many waves of light pass a given point per second? Energy is measured in joules. So when Max Planck calculated the slope of this line, he got this. The slope of this line is 6.626 times 10 to the minus 34 joule seconds. Joule seconds. Why is it joule seconds? Because if you divide the change in y by the change in x, which is how you get slope, it'll be joules over 1 over s. Well, when you divide by a fraction, it's the same as flipping it and multiplying it, which is where joule seconds comes from. You get joule over 1 over s. It's the same as joule times s over 1. And that's where that comes from. You need to know this constant. This is called Planck's constant. It's the constant that relates the color of light to its energy. Basically, if you shine different colors of light on something like a solar cell, you can measure the voltage of the electrons coming off. If they're moving faster, it's higher energy. If they're moving slower, it's lower energy. It's not a complicated experiment. It would have been back then. They didn't have things like ready-made solar panels. They had to find material, rock material that was photoactive. This means that different colors of light have different energies. So come back to Bohr. Bohr looked at, in particular, this was he did the tube for hydrogen. He did the tube for hydrogen, and the hydrogen gave off light in the tube, just like our fluorescent lights giving off light. He passed it to a prism. He saw 4 colors of light. Bohr saw 4 colors of light. And in Bohr's mind, he knew that Max Planck said, oh, I didn't fill in the gap here. Since the y-axis is E, energy, and since if you have no light, you have no energy, he just said, get rid of the B, the y-intercept is 0. And we're going to make it m times frequency. And since m is this number here, and it's called Planck's constant, they gave it the letter h. Don't ask me why, I don't know. So this equation becomes, Max Planck's equation becomes E equals h nu. And all it does is it measures the energy as the function of the color of light. Bohr knew this. Come back to the hydrogen model. 4 different colors come out of hydrogen. Here they actually are. 1, 2, 3, 4. It's 3 different colors or shades of blue and 1 color of red. Now, Bohr says, wait, the atom only has 1 moving part. The proton is huge. So compared to the electron, which is 2,000 times lighter, the proton's sitting still and the electron's moving around it. Rutherford said the electrons are moving around way out there in this layer. Oh, that's wrong. In this layer of electrons, and they're just moving around. Bohr said, wait a minute, hydrogen has 4 colors of light. Light is energy. Light is energy. We can calculate the exact amount of energy based on the color. There's only 1 moving part. In order for the atom to give off light, which is energy, in order to give off energy, the moving part in the atom must lose the energy somehow. And it's always the same color, so it's not a random thing. And so Bohr made this model of the atom. Bohr said, teacher, you're wrong. Rutherford was his teacher. He said, you're wrong. I think it looks like this. Okay, I like your nucleus. But I think all around it, let's see, we had 4 colors of light, right? Well, watch what happens. If I draw 3 rings and I have the electron fall from, say, medium energy to here, it's a very small jump in energy. It's a small change in energy. You can't destroy the energy. You got to get rid of it. So it goes out as red light. If I put an electron up here and it falls all the way down here, then that's higher energy, a bigger fall. So it gives off blue light. But wait, there's another transition. This one could fall from here to here. Maybe that's a medium transition. It turns out the farther you get from the nucleus, the smaller those gaps are. By the way, the gap in energy here, the gap in energy, that's terrible. Let me rewrite that. The gap in energy is called the quantity of energy, or in Latin, quantum. And that's the first time we see the word quantum come into chemistry. When Bohr said that the different colors of light that are seen in the hydrogen spectrum come from the electron falling from higher to lower positions. Kind of like the book. If I drop the book from a high position, I drop the book from a high position. Gotcha. I knew that was going to happen. Versus a lower position. I don't know how that happened. Let's try that again. Versus a lower position. When it falls from higher, it has higher potential energy. When it falls from lower position, it has lower potential energy.
There we go. Good.
She's right. I should. Right next to Kalani over there. Right? I woke you up. Who did I wake up? Oh, good. Yeah. All right. Yeah. They fall so forward. Sleep inducing. So when the electron falls from very high up, it gives off high energy light, blue light. When it falls a short distance, it gives off red light. Now this might be the green light. It might be in between, green. All right. There isn't any green in hydrogen. It's different shades of blue. Maybe that's blue green, right? So that's when he came up with his idea of planetary orbits for the electrons around the nucleus, because the light has to come from somewhere. Now, if you notice, if I put 3 rings, I get 3 colors, right? You can fall from here to here, from here to here, or from here to here. So how do I get 4? How do I get 4 colors of light? Let me try another ring, right? Maybe I just need to put another ring. So I put an electron here. Now watch what happens. When it falls from here to here, 1, 2, 3, or if it's there, there, and there. So in other words, 3 rings, 3 colors. 4 rings, 6 colors. There's no way to get 4 colors of light from this model. So Bohr said, don't worry. Don't criticize my model. It works. He did the math. He used E equals H2. He calculated exactly how far those rings would have to be apart. And he said, okay, according to my model, just like with 4 rings, it says there's 6 colors of light, even though we only see 4. That would mean there's 2. Here's what Bohr said. That would mean 2 are invisible light. That's not like a BS answer, right? What's invisible light?
Like that's invisible.
Right. Very good. Thank you. I'll have astounding. Well, I'll take it. What time was it? Let me show you some invisible light. If you have an Android phone,
Wait, how are we going to see if it's invisible?
because I'm going to convert it. Yeah. If you have an Android phone, if you have an Android phone or your camera on your laptop will also do it. Turn on your camera on your laptop. Apple's won't work because iPhones, I don't know about Mac laptops, but iPhones have a filter to filter out invisible light because they don't want you to have straight light in your picture. Now, our remotes for our TVs and our stereos, they emit something called infrared light. You can't see it.
What's that you're going to turn off?
Oh yeah. Let me try a different one. Okay, you can't see that light, right? But watch what happens when I put it here. Look at that. That's magic. My camera converts the invisible light to visible light. So that's infrared. There's also ultraviolet light that you can't see. They say insects can see it. If you take a picture of flowers with ultraviolet film, flowers are even more spectacular than what they look like in visible light. And so they think bees and wasps and other pollinators, they think that they can see ultraviolet light. So something. So Bohr said, Bohr's model, he added enough rings that he actually predicted like 8 invisible colors of light. Everybody laughed at him. Your model doesn't work. You're claiming there's 12 colors of light, and any fools can see it's only 4. And then Bohr's like, no, it's invisible light. It's light that's either too energetic or too low in energy to see with the human eye. But if you build detectors that can see ultraviolet and infrared, you'll see that I'm right. So they did. They built these detectors. And when they looked at the light coming out of hydrogen, passed it through a prism, and then viewed it with these ultraviolet and infrared detectors, they counted 8 additional colors of light that were invisible to the human eye. And everybody just stood there with their mouths open going, damn, how do you do that? Because nobody knows where he came up with this idea. Nobody knows how he came up with the idea. I mean, he was a smart guy. He didn't have the internet to distract him, I guess. He didn't have Instagram to distract him. He didn't have TikTok. So they had a lot of time to think. If you're a thinker, if you're making a living off gardening or ranching, you didn't have time. Or blacksmithing or leather making. You were always busy. They didn't have Social Security. They didn't have credit cards. You made what you made, and you did. But there were people that were either supported by inheritances or supported by sponsors. I guess in the modern age, called Patreons or something like that. People that pay for you to make videos. There's people that sail around the world and just get paid on the YouTube video channel. Anyway, but back in the day, some people had sponsors, and they were able to sit around and think. Bohr came up with this idea. He was probably paid as a professor, so he had some thinking time. And he predicted 8 colors of light invisible to the human eye. When they checked for it, they verified it, and they said, he's a genius. So they gave him the Nobel Prize. And then they're like, and this guy, he just solved the problem. But what is the atom like? Then they tried doing it for helium, and it didn't work. They tried everything they could to fix this formula and make it work for helium. It didn't work for helium, it didn't work for lithium, it didn't work for any other element. It only worked for hydrogen. Bohr's like, oh, that's easy. Hydrogen's only got one moving electron, one moving part. Helium's got 2, and they interact with each other, and we don't know how to deal with that. So he kind of got out of that. And that's the current understanding. It's like it works for hydrogen because there's only one electron. As soon as you throw that second electron in there, or third or fourth, they all start interacting with each other and makes it very complicated. But there was another problem to Bohr's model that he couldn't get away from. And here's the problem. Why does the electron go from here to here? Why doesn't it just go from here to here? Well, this isn't a structure. There's nothing there physically to support the electron. If it was a moon or a satellite traveling around the Earth or some other planet or the sun, then we can move it up or down just by increasing or decreasing its speed. If we decrease the speed, it falls in. If we
Increase the speed of thought.
actually, if you decrease the speed, it falls in. It's got to go faster at the center to stay up. It can go slower further away. Whatever, you get the idea. So we can move it in or out to an infinite number of positions. So that Bohr's model doesn't explain that. And if it did do that, then what should happen is instead of having all kinds of colors of light, every atom should just basically give off red light because the electrons will just fall in little steps and give off multiple small, energy packets of energy. So it didn't explain that. Why can't it land in the middle? Why isn't it just radiating red light, little clumps of energy and red light? Here's another problem you didn't solve. Why is the electron falling? Why is it falling at all, even if it lands on an orbit? Why is it falling? Because this is negative, that's positive, it's attracted. So why doesn't it just fall all the way and be done? Why doesn't the electron fall into the nucleus? We know it doesn't, because if it did, everything would be neutrons. There would be no life. We're here because it doesn't do that. If it did do that, all the protons would be neutralized into neutrons by electrons. So Bohr's model did not explain this. The person that broke through this problem, they took some of Bohr's ideas and applied it to the new model. Remember, we're going from Bohr to Schrodinger, from Bohr to Heisenberg to Schrodinger. Heisenberg said, oh, it's easy. As soon as you stop trying to think of the electron as a particle, you'll get away from this whole mess. It's not a particle. It's like fiction. It's just energy. It just changes in energy. Whatever. And people are like, what does that mean? How do you change energy without something? So don't worry, my equation works. And Heisenberg came up with what he called matrix mechanics. It was a matrix. If you've done matrices in algebra, you may have seen them. Maybe you remember a matrix looks like this. It's these 2 brackets. You have A, B. No, you have A, B, C, D. And you solve it by multiplying A, D, and subtracting C, B, or something like that. I don't know how to do any bigger than that, but there's ways to do bigger ones. Heisenberg's were huge. They're mathematical formula where those letters represent coefficients in very complicated equations. And his were very, very complicated. And there were only like 2 people in the world that could understand his equations, but they worked. They predicted the colors of light that Bohr did, and they could be applied to other atoms. But most scientists didn't like Heisenberg. They didn't like him saying, forget trying to visualize the atom. It's not a real thing. It's just energy. And I know atoms are real because things are made up of atoms and things are real. So the building blocks need to be real. So along comes a guy named Schrodinger. And Schrodinger said, all right, well, let me back up. Before that, I'm going to take you all the way back to the 1600s for a debate. In the 1600s, Sir Isaac Newton debated a guy named Christian Huygens about the nature of light. Sir Isaac Newton said light is a particle. And you can prove that by shining a beam of light at a mirror, and it will bounce just like a pool ball off a railing. Angle of incidence, angle of reflection equals. Proves it's a particle. Well, along comes Huygens and takes a piece of cardboard with 2 slits in it, 2 very narrow, close together openings, shines a light through it on the wall. I've done it in this classroom with a laser, and it makes what they call an interference pattern, which is associated with water waves. You look down at the bottom of the swimming pool, you'll see shadows of the waves. Even if you can't see the waves, you'll see interference patterns, dark and light patches. Huygens said, see, light is a wave. Einstein came along and said, no, light is both wave and particle. And a guy named de Broglie took Einstein's E equals mc squared equation. Since Einstein said light is both a wave and a particle, de Broglie took Einstein's E equals mc squared equation and said, okay, that's the energy of a particle. And then he took Planck's equation on the other page, E equals h nu, and he said those things have to be equal to each other. Now, when I show you what de Broglie did, and he won $1 million for doing this, any one of you could have done what he did. It was basic algebra. Remember I said C equals lambda nu? That's the inverse relationship, or nu equals C over lambda. I gave you that equation earlier. Now plug this in here, and you get HC over lambda equals MC c squared. Cross out that c with that c. C is the speed of light. Speed of light. And so you get h over lambda equals mc. And de Broglie said, hey, we're no longer talking about light, we're talking about electrons. And so electrons can't go to the speed of light. Let's change c for their actual speed, v. Now you move the m down here, just move it down there, and you get the velocity. No, I'm sorry, move the v down there. Move the v down there. Move v down here, and keep m there. And you end up with an equation that says mass is indirectly proportional to wavelength. And de Broglie says, my equation proves that all particles, including baseballs, footballs, and asteroids and stars, everything is both wave and a particle. Everything has both wavelength and mass. But it's inverse. So if you're bigger than an electron, if you're bigger than the mass of an electron, you look more like a particle. If you're smaller than an electron, you look more like light waves. And Schrodinger said, well, that's Schrodinger said, if electrons are both waves and particles, then that explains why they can't be in between. Here's why. Here's why. The orbits of Bohr's model around the nucleus represent those places where, look at this, see how that boom, that's a collision between two waves. That's not legal. But if you have another distance where you can, I kind of cheated there, but where the wave intersects, the end of one wave intersects the beginning of the other wave, it feeds on itself, then the energy will never disappear. Now, there are multiple positions, like there's a position here where you could go like this. And so this electron here can lose its energy and vibrate slower, like that, but it can't be in between, because in between, you can't get whole numbers of waves feeding into themselves, and they'll destroy themselves. If you've ever heard of, they sell these earphones that actively filter out outside noise, electronic, you have to put batteries in them. What they're doing is they're listening to sound waves from outside, and they create the opposite phase waves that destroy the outside waves in your ear. So you hear perfect silence, supposedly. Anyway, so Schrodinger says electrons are waves. They're waving around the nucleus. And the orbits that Bohr came up with, on average, are the orbits where the waves can feed in on themselves. Clean that up. There we go. Here's another one. Let me do it in blue. That would be that orbit. This one's not allowed because it doesn't feed in on itself. And so Schrodinger came up with this equation called the Psi equation. If you know Greek, the symbol for psi is this. It's called Schrodinger's equation. Obviously, Schrodinger came up with it. If you did Schrodinger, if you reported on Schrodinger, you might have heard me give you a hint. I might have said it. He basically cheated on his wife when he wrote that equation. He took his secretary to a Swiss Alps, like a mountain range in the Swiss Alps, where he rented a cabin. He took his secretary, he banged her, and then in the morning he wrote this equation. What he did was he took all the kinds of things in science that we know about that are wavy. That could be like this. That's if you plot the position of that versus time, it comes out like a sine curve. If you bounce a basketball, when you bounce a basketball, its position versus time is a wave equation, like a sine curve. If you spin something on a string around your head, he took all of these things that behave in a wave-like called periodic functions. Anything that behaved in a wave-like function, he took the equation for their energy, he lumped them all together in this equation called the Psi equation. By the way, psychology is spelled P-S-Y, right? P-S-Y, and it starts in Greek. Psyche is, it starts off with the psi letter. But Schrodinger put all those equations for potential energy and kinetic energy of wavy things together. And when he solved it and then put in the information about electrons, he came up with the energies of electrons as a function of their position, but it was also a function of, it was also probability. Like you couldn't say the electron was always going to be here at this position with this much energy. You would say, I'm 90% sure that the electron is there with that much energy. You could never be 100% sure. And so that's all we're going to cover today. Please, if you didn't do it over the weekend, like I asked you last week, please read chapter 4 tonight. Things are a little complicated in chapter 4 about where Schrodinger's electrons are. By the way, if you take the Psi equation and square it, if you square Schrodinger's equation, it gets rid of negative answers, first of all, and then you graph it. These are the shapes you get up here. These are the shapes you get from Schrodinger's equation. So those are the different vibrations of electrons. The more complicated the vibration, the more complicated the shape, the more energy the electron has. So if you know anything about music, you know that higher energy vibrations are more complex. Okay, guys, online. I'll see you later. Daniel, where are you, man? You there? See you later. Thank you guys for listening.